Hey everyone! Welcome to this deep dive on how artificial intelligence is transforming modern power grid control rooms. Today, we're going to explore all the cutting-edge AI tools and techniques that are helping engineers run a cleaner, more reliable grid. But first, let's set the stage. The global power sector is up against a trifecta of challenges. There's the urgent push for decarbonization, aging infrastructure that can't keep up, and a fundamental shift in how electricity flows around. Not long ago, our grids were a one-way street, a few big power plants sending electricity downstream to passive consumers. Now that model has been blown apart by a surge of variable renewable energy, a flood of small-scale distributed resources like rooftop solar and new high-density electric loads such as AI data centers and EV charging networks. Suddenly, power flows in every direction and can change in an instant. Now, imagine being in a control room watching this chaos unfold. The traditional tools of the trade, old-school energy management systems, and advanced distribution management systems start to look insufficient for maintaining stability in such a volatile, multi-directional grid. They were great when things were predictable, but not anymore. This is where artificial intelligence and machine learning come in. What used to be lofty research ideas are now becoming essential operational tools, helping grid operators make sense of massive data and even automating decisions at lightning speed. We're essentially ushering in the era of the self-aware grid, a grid smart enough to make some decisions on its own, anticipate problems, and optimize itself in real time. To give you an idea of why AI is such a game changer, let's quickly look at the major challenges and how AI is tackling each of them. Renewable intermittency, variable solar, and wind mean less inertia and unpredictable supply. AI solution, advanced probabilistic forecasting and dynamic reserve management keep the grid balanced. Explosion of DERs, thousands of distributed energy resources create two-way power flows and voltage swings. AI solution, new management systems integrated with ADMS and AI-driven volt-VAR control to stabilize voltages. Data deluge, huge volumes of sensor data arrive every second, far exceeding human processing capability. AI solution, intelligent agents filter and prioritize data and automate routine alarm processing. Aging equipment, transformers and lines are getting old, raising the risk of failures. AI solution, digital twins and AI-powered predictive maintenance to catch problems before they cause outages. Electric vehicles and new loads. High-density loads like EV fast chargers and data centers create massive peaks that strain the grid. AI solution, AI-driven demand response shifts and smooths loads to prevent transformer overloads. And that's just scratching the surface. As you can see, AI is stepping up wherever the grid is feeling the strain. In this video, we're going to dive deep into how these AI techniques actually work and how they're being deployed in control rooms. We'll start by looking at some of the core AI methodologies. Things like physics-informed neural networks, graph neural networks, deep reinforcement learning, the nerdy stuff that gives AI its grid-savvy superpowers. Then we'll explore applications in transmission operations, distribution systems, and even cutting-edge tools like digital twins and a new AI assistant for grid operators called eGridGPT. We'll also talk about keeping these AI systems secure from cyber attacks and peek into future tech like quantum computing. By the end, you'll not only understand what AI is doing in the control room today, but also where it's headed next. So let's get started. At the core of this smart grid revolution are specific AI methodologies that help the algorithms understand and respect the physical laws of electricity. In recent years, there's been a big shift away from treating the grid like a pure black box toward hybrid approaches that bake in electrical engineering knowledge. Let's break down three of the most important methods: physics-informed neural networks, graph neural networks, and deep reinforcement learning. So what are PINs? Well, traditional neural nets can sometimes spit out solutions that flat out break the laws of physics. Imagine a machine learning model suggesting a power flow that violates Kirchhoff's current or voltage laws. Not good. PINs fix that by building the physics right into the training process. They integrate the power system's governing equations directly into the network's loss function. In other words, when the PIN is learning, it gets penalized not just for being statistically off, but also for producing any result that doesn't obey core electrical laws. The loss function might look something like this. Here L data is the usual error between predicted and measured values. L physics penalizes breaking the power flow equations, and L boundary might enforce known boundary conditions. By training with this blended loss, the PINN ends up with outputs that are both accurate and physically plausible. A great example use case is state estimation, figuring out the voltages and phases at every node of the grid from limited sensor data. A pin-based state estimator can work even if you don't have a meter on every feeder. Thanks to that physics-informed training, it can fill in the blanks using the laws of electricity as a guide. This approach has been shown to slash errors dramatically. One study reported up to a 97% reduction in current estimation errors using a PINN compared to a traditional method. That's a huge improvement in knowing the true state of the grid, especially when data is noisy or incomplete. Next up, graph neural networks. If you think about it, a power grid is essentially one big graph. You've got nodes and edges. The relationships here really matter. Power flows follow the network connections. Traditional neural nets aren't great at handling that kind of relational, graph-structured data, especially if the grid topology changes due to switching or faults. GNNs, on the other hand, are built exactly for this. They treat the grid like the network it is, learning how connected nodes influence each other in terms of voltage, current, etc. One cool enhancement is using typed graph networks, basically telling the AI what type of node each is. This adds interpretability because the model can learn different behaviors for different components. The neural net knows, for instance, that a generator node follows certain patterns unlike a consumer load node. Using GNNs has led to some impressive feats. For solving the optimal power flow problem, the grand challenge of dispatching generation most efficiently, a GNN-based solver was able to spit out solutions faster than anything we've seen. How fast? It found OPF solutions in a fraction of the time of traditional methods, often showing speedups on the order of 1,000 times over classical solvers. And it does this while still respecting grid constraints, thanks to that physics-informed approach built in. The third big methodology is reinforcement learning, specifically deep reinforcement learning when we use deep neural nets. RL is the kind of AI where an agent learns by doing. It tries an action, sees what happens, and adjusts based on a reward or penalty. Think of it like training a dog with treats, except here the dog is controlling grid devices in a simulation. The distribution grid is a perfect playground for RL because conditions are always changing, solar output fluctuates, loads go up and down, and an AI agent can learn how to react in real time. We usually set this up as a Markov decision process, basically the formal framework for sequential decision-making under uncertainty. We define the state, the actions, and the reward. The agent then uses deep neural networks to approximate a control policy, figuring out what action to take in each situation to maximize that reward over time. Crucially, in power systems we have to be careful. We can't have an AI agent learning by causing blackouts. That's where safe DRL comes in. Safe deep RL means we build in safety checks so the agent never tries a move that would violate operational limits. By adding these safety layers during training, we ensure the AI's clever solutions don't come at the cost of broken equipment or regulatory violations. This kind of learning approach is already being tested for things like Volt VAR control, allowing an AI to find control strategies that human engineers might not even think of, all while keeping the grid stable and equipment safe. So, let's shift to the transmission grid, the high-voltage backbone of the power system. The stakes here are huge. A single failure on the transmission system can lead to cascading outages across a region. Traditionally, operators rely on an EMS to monitor and control the bulk grid. Now AI is supercharging the EMS with faster, smarter analytics and control capabilities. Let's talk state estimation. This is basically the control room's way of figuring out, at any given moment, what the voltages and currents are throughout the grid, a real-time snapshot of grid state. Modern grids have made this task harder. With low inertia and weird noise from inverter-based resources, the classic state estimation algorithms can struggle. They assume things like nicely behaved Gaussian measurement errors, which might not hold true when a bunch of solar inverters are rapidly adjusting and introducing non-traditional noise. AI comes to the rescue by embedding more intelligence into state estimation. Instead of solving a bunch of equations every few seconds, an AI model can learn the spatial and temporal patterns of the grid's behavior. Researchers have built custom neural network-based state estimators that take in raw SCADA and PMU data and output the estimated state. These AI models are trained with special optimization tricks to be highly robust to bad or missing data. For example, in a grid with only a few measurement points, the AI can leverage historical data and probabilistic relationships to infer what's happening at unmeasured locations. It fills in the gaps where traditional methods would throw up their hands. The result is a state estimation that remains accurate and reliable even as the grid becomes more complex and less directly observable by sensors. The next big item is optimal power flow. In simple terms, OPF is like the ultimate juggling act, deciding how to adjust generators, transformers, and other devices to meet demand at minimal cost while respecting all grid constraints. It's central to both real-time operations and electricity market clearing. But as we connect more and more devices and renewable plants, OPF becomes a monster of a math problem. The complexity grows exponentially. Grid operators often resort to simplified approximations like DCOPF, which linearize the problem but can miss important factors like voltage and reactive power limits. AI is changing the OPF game. Instead of solving an enormous optimization from scratch every time, we're seeing AI models that learn how to solve OPF in an approximate but very fast way. Some approaches use advanced meta-heuristics, think genetic algorithms or particle swarm optimization. Others train neural networks on lots of simulated scenarios. There's also growing interest in Bayesian OPF for explicitly handling uncertainty, like random demand spikes or wind gusts, in decision-making. The big advantage of AI. Once you train a neural network to approximate the OPF solution, getting a new solution for the next set of conditions can be almost instantaneous. We're talking milliseconds instead of minutes. That's crucial when you need to redispatch generation quickly due to a sudden event. Moreover, AI-based solvers can handle more complexity. They can enforce physical constraints via their loss function or architecture, like we saw with pins, so they often find feasible solutions even for tricky, non-linear cases where traditional solvers might struggle. They also tend to be more adaptable. If the network topology changes, say a line trips, a well-trained GNN-based OPF solver can automatically accommodate that change without manual reconfiguration. In short, AI-driven OPF has the potential to give us faster, more flexible control of the grid, turning something that used to be a slow offline calculation into a real-time tool. Even with the best planning, things go wrong. Transmission lines can fail, transformers can blow. Grid operators perform contingency analysis, which is basically asking, what if this component goes down, for countless scenarios to ensure the grid can handle them. Traditionally, simulating thousands of what-if contingencies is computationally expensive and slow. AI helps here by learning to prioritize and even predict the outcomes of contingencies. Instead of brute-forcing every scenario, an AI model can identify which contingencies are high risk and focus on those, drastically reducing computation time. It's like triage. Analyze the most impactful potential failures first. Similarly, when an actual fault occurs, AI speeds up fault diagnosis. Machine learning models can chew through the high-speed transient data from sensors, think oscillography, high sample rate recordings of voltages and currents, and quickly determine the type and location of a fault. For instance, by recognizing the signature of a line-to-ground fault on a waveform, an AI can say, it looks like a short on the line between substation A and B, probably due to a tree fall, within seconds. This can dramatically cut down the time needed to dispatch repair crews to the right location. Some utilities have reported significant improvements in fault response times by using ML for fault location, as opposed to waiting for customer calls or manually patrolling lines. Now let's move to the distribution side. the lower voltage networks in cities and neighborhoods where all the rooftop solar panels, battery systems, and smart appliances are popping up. This used to be a fairly dumb part of the grid. Power flowed one way from substations to consumers, but not anymore. Today, consumers can also be producers, hence prosumers. Managing this two-way power flow has become a new frontier for AI. One major task is the integration and optimization of distributed energy resources, DERs. We're talking about solar PV on rooftops, battery storage in homes, electric vehicles, and so on. Each DER is small on its own, but together they add up to big impacts on the grid. Their proliferation demands smarter control. Suddenly, we need advanced communication to handle reversed power flows. AI is great here because it can crunch huge amounts of data to make decisions. For example, AI can help utilities figure out where to install new DERs by analyzing GIS data. It might suggest optimal locations for a community battery or a solar farm that will maximize benefits, like reducing losses or congestion, while minimizing any voltage problems. Then there's real-time operation of DERs. Suppose a cloud covers a neighborhood's solar panels. The local voltage could dip suddenly. An AI controller can react instantly, maybe by telling a battery to discharge power or by adjusting a voltage regulator, to keep things stable. In fact, many DER aggregators use AI models to forecast generation and consumption, allowing them to treat hundreds of homes as one big virtual power plant. They can efficiently trade energy or provide services back to the grid, tasks that historically only big power plants could do. Without AI, coordinating this would be impossible. A specific challenge is maintaining voltage within limits while minimizing reactive power losses, the domain of volt-VAR control. With rising loads and solar, keeping voltage steady is tricky. Traditional VVC methods often fail to account for the variability of solar. This is where deep reinforcement learning has been a game changer. Instead of pre-programming rules, we let an AI agent learn by trial and error the best ways to adjust devices that affect voltage. Through simulation, a DRL agent can experiment with controlling things like capacitor banks or smart inverters to see what strategies minimize voltage fluctuations. Researchers have demonstrated that a well-trained DRL framework can coordinate multiple devices, SVCs, solar inverters, and controllable loads to dynamically balance voltages. Importantly, safe DRL techniques ensure moves respect operational limits. The result is a more efficient network with tighter voltage control, crucial as we integrate more renewables. Microgrids, like a university campus or a remote community that can run independently when needed, bring their own set of challenges. They can connect to the main grid or switch to an islanded mode. This flexibility is great for resilience, but it makes protection tricky. The fault currents and power flows in a microgrid can change drastically depending on its mode. A protection setting that works when the microgrid is grid-connected might not work when it's islanded with only local generation. AI techniques are helping by making protection schemes adaptive. One innovative approach uses machine learning to recognize the microgrid's current operating state and adjust protection settings on the fly. For instance, it might analyze electrical measurements and their correlations to determine if the microgrid is connected or islanded. A hybrid model, combining an artificial neural network and a support vector machine, has been used to interpret these clues and reconfigure the network. This ensures the microgrid remains properly protected, whether it's seamlessly grid-tied or in independent island mode. It's like having a smart relay system that knows when to tighten or loosen protection thresholds based on how the microgrid is operating. Perhaps the most visible success of AI in the grid control room is the move toward self-healing networks. This refers to automating fault location, isolation, and service restoration, FEL-ISR, a process that used to require extensive manual effort. In plain terms, that's the grid detecting a fault and reconfiguring itself to minimize an outage, all without human intervention. Let's walk through what happens when self-healing kicks in after, say, a tree limb knocks down a line. Fault identification. The system first detects that something's wrong. AI algorithms analyze the sudden changes in electrical measurements to pinpoint the location. Isolation. Next, the control system automatically opens switches around the faulted section. This isolates the damaged segment, so the rest stays intact. Reconfiguration. The system then looks for alternate paths. It closes other switches to reroute power around the broken section. Restoration. Power flows again to all customers not on the faulted segment. Everyone else is back online, often within milliseconds. The results are impressive. Utilities like GE, Staden, and Netza BW have adopted self-healing grids with notable success. The key advantage here is speed. While a human might take minutes, AI can do it in milliseconds. That rapid response is a game changer. So far, we've talked about AI making decisions directly. But what about AI helping humans make decisions? Enter eGridGPT, a large language model developed by NREL specifically for the electric grid. Think of it like a specialized AI assistant for grid operators, kind of like a super smart co-pilot. Its job is to digest all sorts of grid data and assist operators by answering questions, explaining situations, and even suggesting possible actions in plain language. The way eGridGPT works is pretty fascinating. It combines language understanding with the power of grid simulations and data analysis. Here's a simplified view of its workflow. Ingestion. It starts by pulling in heaps of data, real-time SCADA measurements, state estimator outputs, contingency analysis results, planning data, essentially a live snapshot of the grid's status from multiple sources. Prompt analysis. When an operator poses a question, maybe something like, "Can we reroute power from substation X to avoid overload on line Y?" eGridGPT interprets the query in context of the current grid state and history. Orchestration. The system can then break the problem down and even write and execute code to get more insight. For example, eGridGPT might generate a Python script on the fly to run a power flow study or fetch outage data. Verification. Before giving any recommendation, eGridGPT validates it using a physics-based digital twin of the grid. In other words, it simulates the scenario or action it's about to suggest to make sure it doesn't violate any grid limits. Human in the loop. Finally, eGridGPT presents its answer or recommendation to the human operator, complete with an explanation of its reasoning, and the human makes the final decision. The operator remains in control. The emphasis here is on trust and safety. You don't want a rogue AI arbitrarily opening breakers. The team behind eGridGPT focused heavily on making the AI reliable and transparent. They trained it in stages, first on general power engineering knowledge, then on specific grid operating procedures and standards, and finally fine-tuned it on the utility's own data. They also made explainability a core feature. eGridGPT doesn't just say Open Breaker 5, it will provide an easy-to-follow rationale, almost like showing its work or a train of thought that led to that suggestion. To further ensure safety, a bunch of safeguards are built into the eGridGPT system. For one, the AI is physics-informed. It also uses digital twin simulations as a sanity check. The system is deployed on premises at the utility. We already mentioned digital twins a couple of times. Let's dig deeper there. A digital twin is essentially a high-fidelity virtual replica of a physical system. For the grid, that means a real-time software model. Operators can use this to monitor conditions and run what-if simulations. It's like having a parallel universe version of the grid where you can test interventions with zero risk. Digital twins are also being used for specific critical assets. For example, a high-voltage transformer can have a digital twin that continuously simulates its thermal and electrical behavior to predict aging. Another example, digital twins of steam turbines use real sensor data to predict mineral deposits. Even in nuclear plants, digital twins of reactor cores can simulate complex phenomena in real time. Digital twins augmented with AI are revolutionizing power grids, providing computational visibility to manage renewable energy. But this digitization is a double-edged sword. As we deploy AI, we expand the grid's attack surface to new threats like data poisoning and evasion attacks. Researchers have shown how stealth attacks can fool AI into seeing a healthy grid as a broken one, or vice versa. However, AI is also our best defense. Agentic AI systems now patrol the grid 24/7, identifying anomalies faster than any human. The challenge is balancing this security with the massive energy demand of the AI data centers powering it all. We must optimize from chip to grid to ensure a sustainable, secure energy future. Another challenge is the workforce skill gap. The ideal grid engineer of the future is part electrical engineer, part data scientist, a combination that's still relatively rare. Utilities are finding it hard to hire. Meanwhile, experienced grid operators are retiring, and decades of knowledge is walking out the door. Capturing that institutional knowledge is vital. AI can help. For example, a chatbot could be fed all operating procedures, becoming a digital repository of veteran know-how for less experienced engineers to query. However, developing such tools and, importantly, getting people to trust and rely on them is both a technical and a cultural challenge. There's also the matter of standards. In the power industry, compliance is king. Take inverter-based resources like solar. A new standard, IEEE 2800, provides guidelines for how these resources must behave to support grid stability. This ensures advanced controls are configured safely. By 2025-2026, new plants will need to meet these requirements. We may also see new standards for AI reliability and cybersecurity. Regulators are watching closely. Looking toward 2030, one technology on the horizon is quantum computing. It's experimental, but could solve grid optimization problems much faster. Researchers are eyeing quantum algorithms for optimal power flow, unit commitment, and intelligent switching, figuring out the best network configuration in real time to prevent overloads. The current thinking is a hybrid approach. A quantum computer handles heavy optimization, while the classical system implements controls. Early prototypes show promise, though hardware is still limited. The vision for 2035 is an affordable, reliable, decarbonized grid. To get there, AI will be indispensable. Future grid operators might resemble airplane pilots using autopilot. They'll oversee intelligent agents and only intervene when needed. The grid will be far more decentralized, with microgrids and EVs, and only AI can coordinate this complexity in real time. The transformation is well underway. What was once electromechanical is becoming an intelligent, self-regulating network. AI and digital twins provide the visibility needed to keep the lights on. The future grid will heal itself, predict failures, and manage the dance between green energy and high demand. It's a challenging journey, but we're reinventing the grid for the 21st century. Key takeaways. As we wrap up, let's highlight a few key points for different folks in the power sector. For grid operators and engineers, AI is providing powerful new tools to enhance visibility and control. Techniques like pins and GNNs mean state estimation and power flow calculations can be faster and more accurate than ever. Automation such as Flisser can restore power in seconds, drastically improving reliability indices. But with these tools comes the need to adapt. operators will increasingly act as high-level supervisors, validating AI recommendations, like those from eGridGPT, rather than turning every dial themselves. Embracing AI means working with it, learning to trust verified solutions while always keeping that engineering judgment in the loop. For planners and utilities, AI opens up new ways to plan and optimize the grid. Machine learning can analyze massive datasets to inform where to site new DERs or how to design more resilient networks. Stochastic planning tools and Bayesian OPF approaches help tackle the uncertainty brought by renewables and EVs. And digital twins can be used in planning to test what-if scenarios, like the impact of a new data center, before investing in steel on the ground. Planners should leverage AI to stress test their plans across many scenarios rapidly, something that was impractical before. At the same time, be mindful of standards like IEEE 2800 and build cybersecurity and interoperability into any AI solution from day one. For researchers and innovators, there's plenty of work to do on the frontier of AI in power systems. One big area is making AI more explainable and trustworthy, developing methods to peer inside neural nets or to rigorously verify their behavior so that operators can confidently use them. Robustness is another key challenge. How do we make AI that can't be easily fooled by bad data or cyber attacks? The integration of emerging tech like quantum computing into grid optimization problems is wide open for exploration. And as always, improving hybrid approaches, combining physical power system models with ML, will yield better accuracy and generalization. Finally, researchers can help capture the knowledge of retiring grid experts by embedding that wisdom into AI systems, effectively passing the torch through technology. The grid needs both domain and data science expertise, so continued collaboration between power engineers and AI experts will be crucial to push the boundaries further. Thanks for joining me on this deep dive into AI in the control room. We covered a lot, from smart algorithms keeping the lights on to the promise of quantum computers on the horizon. The energy landscape is changing fast, but with these new AI tools, it's an exciting time to be in the power sector. Whether you're operating a substation, planning the next grid expansion, or researching the next big breakthrough, AI is going to be a part of your world. Stay curious, stay innovative, and as always, keep the lights on and the data flowing. Until next time, thanks for watching.